Section 6.6 is about exponential and logarithmic functions. Let's start with an example. Consider function y equals 2 to the power x. And let's sketch the graph. So first of all, we see that this function is always positive because 2 to some power is some positive number. So that means that there is no x-intercept, there is y-intercept. When x equals 0, we get that y is equal to 2 to the power 0, which is by the definition 1. So we got 1 point. We also have discussed that the limit of this function when x goes to minus infinity is 0. While on the other side, when x goes to plus infinity, this function becomes infinitely large. So that means that on the left-hand side, behavior of our function is around 0, while on the right-hand side, we have behavior like that. And of course, we can also create some table, the value of x and y. And for example, when x is 1, we get that y is 2. When x is 2, we have 2 to the power 2, which is 4. When x is 3, we got 8. When x is minus 1, we got 1/2. And so the graph looks like that. And it goes to plus infinity. In fact, this graph represents the function y equals a to the power x. So it's kind of typical example when a is greater than 1. And still you see that there is y-intercept when x equals 0, uy is always 1. So this point is kind of fixed point for such family. Of course, there is a natural question, what happens if a is less than 0? So what about if y is equal to minus 1 to the power x? And the point is that this function is not defined because, for example, suppose x is equal to 1/2. Then we get that y is equal to minus 1 to the power 1/2, or is the same as square root of minus 1. And we know that square root is defined only for the non-negative numbers. So a cannot be negative, but what about the situation when a is equal to 0? You can say that y is 0, so it's not a very interesting case, but what if we have a function, but a now between 0 and 1? Again, in case a equals 1, you get that y is just 1. But what if a is between 0 and 1? So typical example, y equals 1/2 to the power x. This function is well defined because a is positive, so no problems with that. But if you try to graph this function, you will see that now, still at x equals 0, y is 1. But now, limit of this function, 1/2 to the power x when x goes to infinity, now becomes 0, because what is 1/2 to the power, say, 100? It's 1 over 2 to the power 100. And of course, this number is very, very small. It means that now at plus infinity, your function is close to 0, while limit when x goes to minus infinity now becomes plus infinity, because what is 1/2 to the power minus 100? You can say that it's 1/2 to the power minus 1 using the property of the powers to the power 100. But minus 1/2 to the power minus 1 is just 2, and so you get that it is 2 to the power 100. And of course, this is a very large number. And so at plus infinity, it becomes very large number, so it's minus infinity. And again, you can create a table with x and y values. So when x is equal to 1, your y is 1/2. When x is equal to minus 1, it's 1/2 to the power minus 1, which is 2. That's what we discussed. If it's minus 2, it is 4, and say it's At 0, it's 1. And so again, what you will see that it looks like that. So it's very similar to this one. You just, in some sense, consider the mirror, the symmetry about the y-axis, and it is in fact true, because what is 1/2 to the power x? Again, I can use the same trick, that it is 2 to the power minus 1 to the power x, or it's 2 to the power minus x. And if you know that there is such transformation, f of x to f of minus x, and this is exactly symmetry about the y-axis. So it's, in some sense, it's not a surprise, but we see that the behavior at plus and minus infinity is opposite. So we have two typical graphs. One is for a greater than 1, and it looks like that. And for a between 0 and 1, the behavior is like this one. Okay, so this is about exponential function. And what about logarithmic function? There is another way how we can express this exponential function. So we'll start again with this. And I'm saying that we can express the same connection between y and x using logarithm. And the connection is the following. If y is equal to a to the power x, we say that x is logarithm with base a of y. It's defined for a greater than 0 because of the reason above, and a is not 1. So logarithm function is in fact the inverse function of exponential function, because this is exactly what it says. If we have y equals a of x, we want to find x. And what is the function that gives me a value of x? This is inverse function. And so another way to define the logarithmic function is to say that logarithmic function is an inverse function of exponential one. Logarithmic function a of x is the inverse function of a to the power x. Okay, so let's see how we can write the same equation in a different forms, or the same connection. We know that 3 to the power minus 2 is 1/9. This is kind of left part of this relation, and we want to express it in terms of logarithm. So let me write it below what we have. We have a to the power x is some number, in this case 1/9. So in our case, x is equal to minus 2 and a is equal to 3. And we want to express it in terms of logarithm of a of x is equal to something. So we see that 3 to the power minus 2 is 1/9 is equivalent to write that logarithm. Here, let me write it like that. This is our connection. So we see that x is equal to minus 2, a is equal to 3, and y is equal to 1/9. And so by this equivalence, 3 to the power minus 2 equals 1/9 is equivalent to the following. Logarithm with the base, which is 3, y is 1/9, and x is equal to minus 2. Another example, suppose we have logarithm of something. Logarithm of 2 with base 32 is equal to 1/5. This is given information, and we want to represent as this connection in terms of exponential function. So what do we have? We have that logarithm of a, and then we have y is equal to x, and we see that a is equal to 32, x is equal to 1/5, and y is equal to 2. And we want to express it in the following way: a to the power x is equal to y. So we see that this thing is equivalent to the following, that 32 to the power x, which is 1/5, is equal to 2. This is equivalent form. Also, we can prove very easy fact that logarithm with any base a of 1 is equal to 0, and logarithm of a with base a is equal to 1. Again, a is positive, not equal to 1. Okay, so let's prove it. We can write down that, again, using our connection, that this is my x and this is my y. So that will correspond to the equation that a to the power x, which is, this should be y and this should be x. A to the power x, which is 0, should be y, which is 1. And of course, we know that any number at power 0 is 1. So it's indeed correct. That means that the initial one is also correct. And the same story happens here. So this is my y, this is my x, and the corresponding exponential form says that a to the power x is equal to y. And of course, also correct. This is first trivial properties, of course, but still they are important. Logarithm of 1 is 0, and logarithm of a with base a is 1. What about the graph of the logarithm? Example, so before we had that x is logarithm of y with some base a. But let's switch to the usual convenient notation of the function, and let's consider y as a function of x. So here x was a function of y, but we usually work with x as independent variable. And let's consider the example y is equal to logarithm of x with base 2. So this is equivalent to the equation x is equal to 2 to the power y by the same relation that we discussed. But here x and y are switched. And of course, we can graph this one. We just should think about our exponential function, but now it is not 2 to the power x, but it is 2 to the power y. So it's similar to y equals 2 to the power x, but you should switch x and y. So for y equals 0, I will get that x is equal to 1. So here's my point. 1. This is x, this is y. For, okay, let me create the table, x and y. When y is 0, then x is equal to 1, because it's x is equal to 2 to the power 0, which is 1. When y is 1, my x is equal to 2. When y is 2, my x is equal to 4. And when y is equal to, say, minus 1, my x is 1/2. Again, you see that when y goes to plus infinity, x is also goes to plus infinity. And when y goes to minus infinity, x goes to 0. So let's put this information in our graph. So I get a function that looks like that. And this is about graph of the logarithm. What are the properties of the logarithms? There are 3 main properties. First of all, logarithm of m times n with base a is the same as sum of the logarithms. Similar story with the ratio of 2 numbers, m divided by n. This is logarithm of m, but in this case it's minus logarithm of n with base a. And the third property is this: logarithm of m to some power k with base a is equal to k logarithm of m with base a. So the last says that you can put the power in front of the logarithm. And in fact, you can prove second one using the third one and first one. But let's prove, say, first one. Let's call logarithm of m with base a by u, and logarithm of n with base a by v. And by our correspondence, it is the same as to say that a to the power u is equal to m and a to the power v is equal to n. But we know that if we multiply m by n, then we will get a to the power u times a to the power v. But one of the properties of the exponential function says that if you multiply exponential functions with the same base, then it will be sum of the powers, a to the power u plus v, right? So what we get? We get that m by n is equal to a to the power u plus v. And using our equivalence, that corresponds to the following, that u plus v is equal to logarithm of the product. But we defined our u as logarithm of m with respect to a with base a, and v as logarithm of n with base a. So that means that logarithm, so my u is logarithm of m with base a, and v is logarithm of n with base a. So we get desired property. Suppose you have a to the power 3 is equal to 2. Okay, this is our exponential form. What is the corresponding logarithm form? Of course, you can just follow the rule that we discussed, but you can also think in the following way. Let's apply logarithm with base a to the both sides. A cube logarithm of 2 with base a. Then logarithm of a with base x is the inverse of a to the power x. That means that logarithm of a of x is equal to x. This is the equivalent. This is just the definition of the inverse function. Of course, you immediately can see that if you believe in the third property and the property that we just discussed. So what I'm saying, so it's kind of proof. In fact, it's not a proof, but at least you will see that everything matches. Logarithm of a to the power x with base a using the third property, right? I can put x in front of the logarithm. So it's x logarithm of a with base a. But we also prove that logarithm of a with base a is equal to 1. So this is 1. And so we get that logarithm of a to the power x with base a is indeed x. And how to apply it? We have that 1 logarithm of a to the power 3 with base a gives me just the power of a, which is 3, right? While on the right-hand side, I got logarithm of 2 with base a. And this is exactly my logarithmic form. So I could use my rule that I discussed at the beginning and say that a to the power 3 is equal to 2 is equivalent to the statement that 3 is logarithm of 2 with base a. But from my point of view, it is easy if you think about logarithm as the inverse function of the exponential function. This is one way how you can get logarithmic form from the exponential form, but of course there is the second way from the logarithm form to the exponential one, and it uses, so remember that if you have function and inverse function, then not only f of inverse function applied to x is just x, but also inverse function of f of x gives you x. So it's two conditions. And so we discussed one. So I applied logarithm to the exponential function and get x, but of course you can apply exponential function to the logarithmic. So what I mean that a to the power logarithm of x with base a will give you x. Okay, let's consider another example. Suppose you know that logarithm of 4 with base a is equal to 1/2, and you want to find the corresponding exponential form. So for that reason, you consider a to the power of left-hand side is equal to a to the power right-hand side. Okay, so what you get? You get that, so this is another example, a to the power logarithm of 4 with base a is equal to a to the power 1/2. But because of this definition of the inverse function, that gives you just 4. And on the right-hand side, it's a to the power 1/2. So you get the exponential correspondence. Again, this is the same if you follow our initial rules. Okay, let's do more examples. So suppose you want to write the following expression: 2 logarithm of x with base a plus 3 logarithm of y with base a minus logarithm z with base a as logarithm with base a of something. So just in terms of one logarithm, single logarithm. So how to do that? First, I will use third property. Remember that the property was logarithm of m to the power k with base a is equal to k logarithm of m with base a. But I will read it from right to left. So I have k in front of that, and I can put it inside the logarithm as a power. So by the third property, it is logarithm of x squared with base a. Okay, the same story happens with logarithm, 3 logarithm of y with base a. Again, by the third property, I can put 3 inside as a power and get that it is logarithm of y cubed with base a. And with last one, I don't need to do anything. Then 2 logarithm of ax plus 3 logarithm of ay, this is first part of that, becomes logarithm with base a of x squared plus logarithm of y cubed with base a. Then I use second property of the logarithm that says if I have product of numbers, then the logarithm of them is sum of the logarithms. And again, I will read it from right to left. So if I have a sum of the logarithms, I can write it as logarithm of product. So it's logarithm with base a of x squared and y. And so my expression now looks like this. It's logarithm of x squared y with base a minus logarithm of z with base a. Oh, sorry, it's not second. I think it was first one. Now I can use second. And second one says that if I have logarithm of the ratio, then it's difference of the log. So minus the denominator. That's how you can remember that. Okay, so this is my second property. And so I can express it as logarithm of the first one as a numerator divided by second one, which becomes denominator. So again, I'm reading a second property from right to left. And I am done because now I have only one logarithm, single logarithm of x, y, and z. I forgot that it should be cubed. Y should be cubed, sorry. Why should be cubed? Because I copied it in the wrong way. Okay, that was the example. Let me make some remark that it is important that base should be the same if you want to use properties. What do I mean? I mean that there is no simple way to do something with logarithm of x with base 2 plus logarithm of x, the same x, but with base 3. Because so you cannot write that it's logarithm of x squared, but what is the base? Is it 2? Is it 3? Or is it 6 of x squared? The point is that it's none of this. So the base should be the same. If you look at the properties, you see that everywhere A, and A. So base is the same. But let's do other direction. So suppose you have logarithm with base 2, 1/4 square root of x. And you want to break up this logarithm into sums, difference, or multiples of logarithms. How to do that? Again, using the properties. So first of all, I can write that this logarithm is the same as a logarithm with base 2 of 4 square root of x to the power -1. And then using third property about power, that I can put power in front of the logarithm, it's -1 logarithm is base 2 of 4 square root of x. Next step, I see that I have a product of 4 and x, so I can use first property for the product. Logarithm of the product is the same as sum of the logarithms. So it is -1 times logarithm with base 2 of 4 and plus logarithm with base 2 of square root of x. Square root of x I can furthermore simplify, as well as logarithm of 4 with base 2. Because this is the same as -1 is common factor. Logarithm, what is 4? 4 is 2 to the power 2 plus logarithm 2, and square root of x is the same as x to the power 1/2. And now it gives me -1. Logarithm, again, I can put 2 in front of the logarithm using the third property. Logarithm of 2 with base 2 plus logarithm plus 1/2 power logarithm of x with base 2. But again, we got logarithm of 2 with base 2, it is 1. And so my final answer is equal to -2 minus 1/2 logarithm of x with base 2. Logarithm function can help us to solve some equations like this. Suppose you have an equation 271 to the power x is equal to 468. And you want to find x. And how to do that? Of course, using the logarithm, there are two ways. Consider logarithm with base 10 of left-hand side and right-hand side. And then what we will have? We will have that a logarithm with base 10 of the left-hand side, which is 279 to the power x, is equal to logarithm with base 10 of 4.68. And thus, using the third property, I can put x, because it's a power, in front of the log. and get that it's x times logarithm of 279 with base 10 is equal to logarithm of 468 with base 10. This is some number and this is some number, so I get basically that x times a is equal to b, and thus x will be logarithm of 10, logarithm of 468 with base 10 divided by logarithm of 279 with base 10. Second way, again, it's using the fact that logarithm is inverse function of the exponential function. And let's apply the logarithm with base 279 to the both sides again. And so here, again, I have logarithm of the same exponential function. So this is, again, function of the inverse function, and that gives me just x. While the right-hand side gives me some number, logarithm of 468 with base 279. And this is final answer, so just one line. But of course, there is a reasonable question. We get x is equal to that, and we also get that x is equal to logarithm with base 10 of 468 divided by logarithm with base 10 of 279. So they look very differently. But in fact, logarithm of with base 279 of 468 is the same as logarithm with base 10 of 468 divided by logarithm with base 8 279. And this is not the coincidence. This is the general fact, which is called change of the base. And the statement is the following. Suppose you have logarithm b with base a. Then the claim is that this is the same as logarithm of b with any base c divided by logarithm of a with base c. So for any a, b, c that are greater than 0 and not equal to 1. So in our case, a was 278, b was 468, and we choose c equals 10. Because remember, for some reason, I chose logarithm with base 10 when I solve it in the first way. But again, I could choose any base, say logarithm with base 5, with base 200, whatever, and I will get the same answer, but the base would be different. And this theorem proves that, in fact, it doesn't matter what is the base. I mean, in general, it matters, but if you have such ratio as on the right-hand side, then it doesn't matter because it's equal to logarithm of b with base a. And so in our case, if we plug a, b, and c, we get exactly what we wanted. Such logarithm is equal to logarithm of 468 with base 10 divided by logarithm with base 10 of 278. Okay, and also it's worth to mention that exponential function is continuous and logarithm with fixed base is also continuous. And we remember that for the continuous function, we have that the limit when x goes to some point x naught, f of x can be evaluated just by plugging this x naught into function for continuous functions. And so limit when x goes to x naught, logarithm with base a f of x is equal to logarithm of f of x naught with base a. Or maybe I should add one more step, that's logarithm, and limit can be interchanged. So it's logarithm of a and then limit f of x when x goes to x naught, and that gives you f of x naught if function is continuous.